Okay, cool. So let's start after break. I was supposed to put up problem set 2, but I haven't gotten around to doing it. Uh, so it's possible that today's lecture may be a little shorter because the only thing that I plan to do today is just analyze the zigzag product and build expanders from it. Okay. I mean, these are things where I think the proofs per se are actually quite short, but I think it takes a little bit of time to internalize what exactly is going on, and having different perspectives help. Okay, so standard recap. This was our definition of lambda, which refers to the second largest eigenvalue besides the trivial eigenvalue, and the spectral gap was defined as the gap that lambda has from 1. And what are we trying to do? We are trying to build a family of regular graphs, d-regular graphs, and you're usually okay with it as long as d is some constant. Okay, but the way the family is sort of, way you like to build these things is like you're usually given some target spectral gap that you want to achieve. And you want to build a family of graphs, each of which has at least the spectral gap that is expected. Like whatever gamma that you want, that spectral gap exists. And
you just started, right?
Yeah. And then the number of vertices is sort of it's increasing. Like as I become larger and larger, these are graphs on larger and larger number of vertices. They have the same degree, they're irregular, but they have better and better. So rather, they have at least some guarantee on the spectral gap. Okay. Eventually, we'll also sort of say that I also have a target n. And I would like a graph that has roughly n vertices. Maybe I'm okay with, instead of n, if you give me a graph on 100 n vertices, I'm okay with it. But if you tell me that I'll give you a graph on either n minus 1 vertices or 2 to the n vertices, that's sometimes not helpful because you may not have the graph of the right size. Okay. And we're going to sort of measure how explicit this graph is based on how quickly you can compute a neighborhood relation. That is, I give you a vertex u, and then let's say I ask you for the jth neighbor of u. I want to know how much time will this take. Okay. And in the weakly explicit setting, you would say that I want this to be run in polynomial time in the size of the graph. So if the graph is on ni vertices, I want it to run in poly in ni. But like we mentioned last time, I mean, we would sometimes be building these graphs in a sort of implicit manner, in the sense that
for every u it should run in poly.
Yeah. By this I mean, like, think of this as input star, it should run in this much time. And for strongly explicit, what I want is I want it to be polynomial in the input length. And the input length in this case is just a vertex label and a degree label. And therefore, I want it to run in poly log number of vertices. Okay. So
here, your input is also I.
Yeah, so I is, I mean, the degree is never going to be more than n, though in principle it can with self loops, etc. So I'm assuming that the degree is much smaller than n in some sense, so therefore the input size is dominated by the number of vertices. Log of the number of vertices. Yeah. Okay. And something that we saw last time was this very nice matrix decomposition, which sort of characterizes whether or not your graph corresponds to a gamma expander or not. And it basically sort of says that you can decompose your matrix into gamma times the complete graph matrix, which is like every entry is 1 over n in the case of d-regular graphs, and 1 minus gamma times some matrix E, where the guarantee is that the spectral norm of E is at most 1. And just to recall, what is a spectral norm? This is the maximum value of Ex over X, because X not equal to 0. Okay, that is how much does the matrix possibly stretch any vector. Okay, so that's what E is, and this sort of the intuitive description of this equation is that an expander is basically, it's like a convex combination of the complete graph and something that doesn't mess up too much and some error term. And how close you are to a complete graph is sort of it's tuned by how good your gamma is. The larger the gamma, the closer you are to a complete graph. Okay. And last time we saw a bunch of graph operations. So the first example of this graph operation was this. So let's say G is some ND gamma graph. We defined this G squared, which was a ND squared comma something graph. Okay, where every step in G squared is 2 steps in G. Okay, so this was roughly what we saw last time, and it's easy to sort of see that lambda of G squared, this is equal to lambda of G the whole square. So therefore, this is going to be 1 minus of what should this be? 1 minus of 1 minus gamma squared, or 1 minus gamma the whole square. Something, I mean, like, so this is going to be 1 minus of. So in some sense, this is something where either you think of it as your eigenvalue drops, which means your spectral gap increases. Okay, and so this was the graph G squared, and it's sort of a very natural thing. Again, there's nothing special about square. You could have done this for any higher power also. And what is the plus? What is the good thing that this operation does? It reduces lambda, which is the same thing as increases gamma. So the spectral gap that you want is getting larger, but the bad case is that this increases degree. So whatever, if the old degree was d, though now the new degree is like d squared in the process. So the degree is getting worse in this operation. Okay. So the next operation that we saw was this notion of tensoring, which is like you're running 2 graphs in parallel in some sense. So what is this graph? The vertex set is all, let's say, u1 comma u2, where u1 is a vertex in G1 and u2 is a vertex in G2. Okay, and you connect the pair u1 u2 with v1 v2 if u1 is connected to v1 in the graph G1 and u2 is connected to v2 in the graph G2. I'm right now writing it just as an edge relation, but technically speaking, you could say that the I1 I2th neighbor of u1 u2 is going to be, you take the I1th neighbor of u1 and I2th neighbor of u2 and just think of that as the pair. Okay, so this is a graph on what? This is a graph on n1 n2 vertices. The degree happens to be d1 d2, and something that we saw last time was that the spectral gap is at least as large as the min of these two. Like whichever was the worst expander, this is no worse than that. Okay, I mean, like that's the guarantee that you have here. So this operation has this nice property that the plus point is that the number of vertices increases, and this thing gamma didn't get worse, didn't get, let's say, too bad. That is, whatever was the worst of the 2 graphs, now your larger graph has that sort of spectral gap. But again, the negative is that the degree increases. Okay, so both of these were situations where you seem to be either improving the number of vertices or the spectral gap. But unfortunately, both of these operations are making the degree worse. And we want some mechanism to bring the degree down. And the part that we are going to analyze now is the zigzag product that we mentioned last time. So let me just recall what the zigzag product is. So the setup for the zigzag product is that the two things that you're taking a product of, they must be compatible in some sense. What does the compatibility mean? I want the number of vertices of the second graph to be equal to the degree of the first graph. Okay, it's only then that the zigzag product is even meaningful. Otherwise, this product is not even defined. And now this is going to be a new graph on ND vertices, which we are going to think of as again pairs of the form U comma A, where U is a vertex. U is one of the original vertices of G, and A is something in 1 to D, which I'm going to think of in two different ways. There are situations where it will be convenient for me to think of this A as either a vertex in the graph H, or I might also think of this as an edge label for the graph G. By an edge label, what I mean is, imagine being on a vertex, it has D spokes going out, D edges going out, and you can think of A as indexing one of them. And this two different perspectives is going to be quite helpful. And what is the rough picture that we had here? So let's say this was a vertex U, and this was a vertex V, and this was one of the edges in the graph G. I don't know, maybe the graph is, I don't know, 5 regular or something. Okay, so U and V have 5 other vertices going out, in which case H is now going to be some graph on 5 vertices. Okay, and the way I'm going to think of is like I think of removing this and creating a small cloud in these two places where the edges of H sit here. Okay, and it will be convenient to think of this as the cloud of U and the cloud of V. So the cloud of U consists of one copy of H in some sense, and the cloud of V consists of one copy of H. And the specific edge UV that you had in G, there is some vertex on cloud U that is sitting at one endpoint, and there is some vertex on cloud V that is sitting on the other endpoint. Okay, so let's mark those two things. Maybe this is like, this vertex is A, and this vertex is B. So the new zigzag product, these are the vertices of the zigzag product. So there are ND many vertices. And now what are the connections? And the connections basically says the following. It says that no, if your rotation, if the Ath edge out of U is the Bth edge into V, that's the same thing as saying this particular UV edge, like it's the two vertices of H that are sitting in those respective clouds are A and B respectively. Okay. Then it basically says, what are the connections that I'm going to draw? Well, look inside the cloud of U and look at the neighborhood of the vertex A. That's some set of points. Similarly,
there is the line, the side
inside H.
Inside, sorry, first project.
Yeah. So in U comma in the Yeah, so basically I want
those two views, no?
Yeah. So basically I want to say, look at the neighborhood of A inside H restricted within the cloud of U, and look at the neighborhood of B inside H restricted to the cloud V. So there are D vertices here and D vertices here. You connect all of them. Basically put a complete bipartite graph on them. Okay, so in this case, this vertex is going to get, so this will be connected to this will be connected to this will be connected to this, and this will be connected to this. So the red edges are what are the edges of the zigzag product. None of the black edges exist, none of the blue edges exist. The only edges in your graph are these red edges. Okay, so this was the definition of the zigzag product.
So here we are assuming that H did not, it's a simple graph, right? It does not have self loops.
It could have self loops.
So then, A would itself be a neighbor of A and B.
Yeah, in which case you will connect.
Would come back to that.
Yeah, in that case, you will probably connect this to this as well. Like, for example, let's assume that B also had a self loop on itself.
Yeah, that's correct.
In which case, you connect those two. So, whatever is the neighborhood, whatever that multiset is, you connect that multiset with this multiset. You just put all possible things between. Okay. And something that we noticed last time was that this new graph, of course, it's a graph on capital ND vertices by construction. And it just takes a little bit of thought to convince yourself that it actually has a degree d squared. And in fact, it was sort of The better way to see that the degree is d squared is to think of, if you were to do a random walk on this graph, what would you be doing? Okay, so you will be starting at some vertex u comma a. What is your random walk supposed to do? It will basically stay inside cloud of u, but instead of a, it will say, let me pick a random neighbor of a within that cloud. Okay, so I have d possible choices. So I move to u comma a prime now. But that a prime leads to one of the g edges to a different cloud, possibly. I reach somewhere there, and then I take one more random. So in some sense, I have d squared choices. I have d choices for the first thing and d choices for the second. Okay, anyway, we'll see this shortly. So the thing that we didn't analyze last time, though we just sort of mentioned what this is like, I want to get a sense of what is the spectral gap. If I'm told that G and H have some spectral gaps, gamma 1 and gamma 2, what sort of guarantee can I give about the spectral gap here? So in order to get a sense of what the spectral gap is, it's actually the first thing we need to get a sense of is what is this matrix? If I were to think of this as a random walk matrix, is there an easy way to just write down this matrix and somehow analyze them after that? Okay, so something that we spoke about, I sort of said that this is something you should think of as to what happens in this very, very special case. Okay, because it's going to be convenient to have this intuition, which is, let's just assume that for this, now just to get some sense of what is going on, let's assume that the inner graph H is actually the complete graph on capital D vertices. And I mean complete graph with self loops at every vertex. Basically, it's the one that corresponds to the all ones or all 1 by n, all 1 by d random walk in this case. Okay. In that situation, if you were to look at the zigzag product, what will the zigzag product be? What will the underlying graph be? So maybe it helps to look at this picture. So now imagine this,
every cloud
all clouds, like let's imagine that every vertex within a cloud, they're all connected to each other by edge. That's what the complete graph here means. Which means when you are putting a complete bipartite graph between the neighborhood of A and the neighborhood of B in those two respective clouds, what are we going to be doing now? You're basically going to connect everything in that cloud to everything in this cloud.
So the operation is that you just replace every vertex of the original graph by a cloud, and if there is an edge in the original graph, you put a
complete graph. So if you want to think of it as your random walk is doing the following. You start off at u comma a. You truly go to a random neighbor of u in the graph G, which is, you'll now be in cloud V right now. But you completely disregard what A was and just randomly resample your B. Right? That's what the random graph sort of looks like. Like in the second coordinate, it's completely mixed. And on the first coordinate, you are doing your walk as you were doing it on the graph G. Now, what does this remind you of? This is a graph operation we have seen on. Every step now looks like you take an honest to God step in G. But as far as the step in H is concerned, you completely disregard everything and then you just mix completely. So I want to claim that this is a tensor product of something with something. I just want to get a sense of it's a tensor product of what with what. So it's like the
all one with
yeah. So basically, this is nothing but this is the same thing as G tensor product with KD. I mean, in the sense that we have seen tensor products.
Oh.
This is a special case of a tensor product in the sense that the zigzag product and the tensor product actually coincide. I mean, in this specific instance, when your H graph was completely connected, what you end up doing is like saying that you start with a pair u comma a. What is your new neighbor? You replace u by a random neighbor of u. But as far as the A part is concerned, you just replace it by a random. So that's like as if you took a tensor product of your original graph G and the complete graph in some sense. So naturally, I mean, like, so this part, it somehow feels like what is happening in the second component was sort of independent of what was happening in the first component. The zigzag thing is somehow trying to connect the two together. But in the specific instance, when H is a complete graph, the zigzag product of G and the complete graph is the same thing as the tensor product of G and the complete.
A very basic question about the zigzag product. So you start off with the graph of G, and every vertex is replaced by a copy of H.
Yeah. So locally.
So now, so let's say you had this U to V.
Was a particular edge in the graph G.
Now so now you took some A and B from those H copies and you connected them.
So in the sense that the edge UV was, let's say, the eighth edge out of the vertex U. I mean, there are D edges.
How did we figure out once you place a copy of H inside G? I mean, you could have chosen any of the vertices from that copy of H to be the.
You could. So basically come up with some reasonable labeling. You know that the number of edges going out of G is like capital D.
Yeah.
The number of vertices in H is also capital D. So you had some notion of saying that this is my first edge out, second edge out, third edge out or something.
Okay.
Maybe use the same label for that. The actual labeling doesn't matter, but it's just convenient to sort of work with both of these things.
Sure.
So now you know that from the vantage point of the vertex U, there is an H vertex sitting on every edge that is going on.
And you connect.
Okay, so now, like, if there was a G edge, where there is a vertex sitting here and a B vertex sitting there, you connect their neighborhoods within those clouds by a complete bipartite graph. So that's what was happening here. And in the case when you are dealing with a complete graph, this is like as if you're basically just going to connect everything in that cloud to everything in this cloud, as long as those two clouds are connected. Okay, which is the same thing as the tensor product of the original graph with this. So this is something that we will encounter soon, because we are going to try and move to this situation. Okay. So now what I want to get a sense of is, if I wanted to take a random step inside the zigzag product, I want to know how would I go about doing this, because I'm trying to build the matrix that corresponds to the zigzag product. So I'm trying to decompose them into parts and sort of say, okay, this is what I would be doing. So let's say we start at a vertex.
So now you're back to H, not KD.
Yeah, I'm sorry. I am back to, in general, you're dealing with G zigzag H, where H is some arbitrary graph that is compatible. And I want to know, if I were to start a random walk, that is, I just take one random step in the zigzag product, how do I go about doing that? And the way we have constructed it, it actually sort of breaks up into three different steps. Okay, because it's like every edge corresponded to a three-step walk that was happening, and we're going to write that down carefully. So what do we first do? This goes to U comma A prime, where this is a step in H. That is, from A, I go to a random neighbor of A, which is, say, A prime. Okay, so where A prime is a random neighbor of A in H. That is, in the graph H, just take a random neighbor.
So, I'm a bit confused. You are defining a random walk in this graph, is it?
So I'm doing this. I'm going to do a random walk in the same way I have defined this graph. So
eventually, you're going to say that this thing is equivalent to a random walk defined on this, because a random walk on a given graph, irrespective of how it arose, is just whenever you are in a vertex, you take a random neighbor.
That's right. So now
now
basically I'm saying U comma A has D squared neighbors in the zigzag product. Right? And I'm just going to get to one of those D squared neighbors. I'm breaking up that choice into two different choices. Because the construction itself was like, you first have a choice of D, and then you do something deterministic, and then you have.
So there were in the old graph, there were these blue edges. The blue edges do not
are not there in the zigzag product at all.
Right. So if you are in a.
So I want to know U comma A, there are D squared neighbors of U comma A, and I want to know what all are they.
Right.
Okay. And what are the neighbors of U comma A? Like
I mean, therefore, there is no connectivity between U comma A and U comma A prime.
No. There is no connectivity between U comma A and U comma A prime.
Yeah.
I am mentally imagining.
Yeah, I say reconcile that this is the new way of looking at the random walk is exactly
equivalent to whatever was the
graph.
That's right. That's right. So maybe
if we are at some U comma A, then all the edges in the zigzag product came like every edge corresponds to U. So you look at every neighbor that you have, and each of those neighbors led to you having D.
Okay, so maybe let me do the following. Rather than writing this as neighbors, I'm going to basically tell you if I were to ask you the following question. Okay, so this is the zigzag product. I'm looking at the vertex U comma A, and I want to know what is the I1 comma I2th neighbor of this vertex. This is what I want to know. And I want to get a sense of how am I going to compute it. Okay, and the graph was constructed, like almost felt like it was a procedure to tell you what the I1, I2th neighbor was. And we are going to execute that procedure now. Okay, and this happens in 3 steps. Okay, so this U comma A, you sort of mentally imagine this going to U comma A prime, where now this is not a random neighbor, but whatever, gamma h of A comma I1, this is equal to A prime. That is, if I look at the I1th neighbor of the vertex A in H, it is some other vertex A prime. Okay, so that is like saying that.
So strictly speaking, the graph was not constructed in this way, right?
I'm thinking of this as saying that now imagine, I mean, the role of A and A prime have sort of shifted right now.
But everything is not underneath. Not visible.
So here, okay, I'm just going to erase these things. This is not the color I wanted. This is this. So I want to imagine, suppose this was my vertex A.
Yeah.
Like from this, I have one of these 2 vertices I could have gone to. Right? Those are 2 of my neighbors, but there are other neighbors that I may have from other ways also.
Other clouds,
etc. But one way to get to one of these 2 vertices is to basically take a random neighbor of A, which in this case, let's say, is equal to A prime. So the random neighbor of A, here, suppose I chose A prime as my random neighbor.
All the edges to this cloud from A to a certain cloud arrows out of A prime.
Arrows out of A prime. Okay. So I went to A prime and mentally imagined going to A prime, took the only edge that I could take, only G edge I could take at this point, reached here, and now I have again 2 choices.
Correct.
So I choose one of the 2 choices. So I have D choices for the first thing and D choices for the second. And that's what I'm trying to write this as. Okay. So the first thing that I do is like I mentally imagine taking that in like intra-cloud step. Okay. And now I need to go from U comma A prime. This is actually no longer random. In fact, there is only one choice that I can do. This will go to some B comma B prime. Okay. The only G edge available. Oh, sorry, this is not 2. This is step 2. And what is step 3? And now I go from V comma B prime to V comma B, where gamma h of, B prime and 2, this is B. So this is the process of going to a random neighbor. When I mean a random neighbor, all I'm going to say is that this I1 and I2 are going to be picked at random. And then you just follow this process.
It just shows that the graph of the is D squared.
Is D squared regular? I mean, of course, there could be multi-edge. I mean, like maybe there are multiple paths to the same this thing.
No, it's small D squared.
Yeah, it's small D squared regular. Okay. But okay. So now what I want to do is I want to imagine these as 3 different matrices. Like imagine doing the first one as a random walk. You make one step. And then doing the second one, and then doing the third one. I'm going to call those matrices as M1, M2, and M3. And I want to get a sense of what is M1, what is M1.
First and the last matrix.
First and the last matrix are the same because the operation is still the same. You stay in the same cloud, you move to a random neighbor in the second coordinate.
The edge.
Okay. So what is the matrix M1? Okay. So basically, I want to sort of say, suppose I give you a vector of length nt. This is the current probability distribution of where I may be. But it makes sense for you to just get a sense of what does it do to the point distributions. Now, suppose I was at a certain vertex. Okay. And I want to apply the random walk matrix and now go to whatever is this new vertex, this new distribution. So what should I be doing?
The identity tensor.
Yeah. So basically, this I want to claim just looks like this. So so this is like basically I'm writing it in terms of clouds U1 through UN, U1 through UN, and inside each block is sort of broken up into the edge components. So what happens here, if I start off at a certain cloud, of course I have to stay in the same cloud. But now within the cloud, I change my second coordinate like as if it's a neighbor. So what am I allowed to put? So basically this is just going to be MH, MH, MH. And the rest are all 0. That is, you have no opportunity to change your cloud at all. But within a cloud, you move to a random edge neighbor. And this is just a fancy way of, this is just I tensor MH. I mean, if I were to be very careful, I need to write it as I subscript N tensor MH, etc. But there'll be way too many subscripts and it'll get this thing. Okay, fine. Okay, so it's an N cross N identity tensored with the random walk matrix of H, which is a D cross D matrix. Okay, so this is the same thing for M1 and M3. That is the matrix that corresponds to the first step and the second step.
In step 2 here, why did it say the only GS?
So here, what I mean by that is like once I'm at this vertex.
You're going to the eighth neighbor of.
No, I started from U comma A. I took a random neighbor, I've gone to A prime. Now there is an A primeth edge out of the cloud U.
Dictated by G.
Dictated by G, right? I mean, like. So the A prime sort of labels a certain edge going out of the vertex U. So that's the only edge I have to take. That and lands up in some other cloud.
Picture the black color.
Yeah, that's the black colored edge.
Like when we started by constructing this G zigzag edge, like we looked at every vertex in G, like just sort of looked at these incoming edges as points, and we put some orientation of edge onto it.
Yeah.
Once you fix that, then
once you're at A prime, there is a notion of the A primeth edge going out of the cloud. And that's the edge I have to take. You take that edge, you land up somewhere. And maybe you now land up at V comma B prime or V comma whatever. What did I call it? V comma B prime. And at B prime, you will take random neighbor. Okay. Now, what about step 2? If you were to think of this as a matrix, what is this? Or if you think of this as an operation that takes U comma A prime to V comma B prime. What is this operation? Firstly, it's a completely deterministic thing. It doesn't care about I1 and I2 at this point. Right? The I1, I2 didn't matter. But this is an operation we did briefly mention last time. So what is this?
come up.
Yeah. So this is basically the rotation map. You are saying I go from u comma a prime to v comma b prime to indicate that v was the a primeth neighbor of u and u is the b primeth neighbor of v. So therefore, what you're doing in step 2 is just applying the rotation map. Okay, but of course I need to think of this as a matrix now. Okay, so this is just rotation map as a permutation matrix. That is, whatever probability mass that you have here, you're just you're shuffling those coordinates to move to the corresponding this thing. It's like, imagine that someone had put there was a certain probability with which you could have been in this thing. Now, after applying the rotation map, the probability of being in this vertex is exactly that. You're basically just applying a permutation on ND coordinates, where every coordinate is getting matched to the rotation map wala coordinate. Okay, so this, I just want to say that this is the rotation map where, so each row, so if I think of u comma a here, okay, so there will be exactly 1, 1 in that row. The rest will all be zeros. And at which coordinate will this be? This will be some v comma b or something. In fact, let me put a prime and b prime because that's what we had here. U comma a prime going to v comma b prime. There is a 1 in that particular coordinate if and only if rod g of u comma a prime equals v comma b prime. Is that okay?
Sorry, so how did you compute rod g when you were given a u comma a prime?
So, I mean, G had some rotation map. There was a notion of, you could always say that, my ith neighbor, okay, maybe the ith neighbor is a vertex V. But the edge you took to go into V, that is, V calls it something. I mean, V calls it some B prime. So the rotation map of u comma a prime is equal to v comma b prime if both u and v with respect to a prime and b prime are referring to that same edge. Okay, so that's what we mean here. And as a matrix, you can think of this as a permutation matrix, where each row has exactly 1, 1 in it. And where do you have the 1? Well, you have the 1 corresponding to the column, which is the image of your rotation. So that's this new matrix. Okay, so that's what this is. So what does this together tell you? This tells you that the random walk matrix of the zigzag product is actually these 3 steps put together. So this is going to be I tensor H, that's step 1. And then you apply the rotation map. I'm going to write rod G, but what you should think of that as a permutation matrix. It's an ND cross ND permutation matrix. Okay, times I tensor H.
And the rod G map is not like actually a rod G tensored with
no, it's actually on ND vertices. It's on ND vertices. All the 3 matrices that I have written right now.
Not sure, but you can't decompose rod G as a permutation on G tensored with an
I mean, it's unclear how the labeling sort of work. I mean, like, I'm not expecting the labeling.
I don't see it.
Yeah, I don't think there is a way of decomposing that in any nice way. Okay, so this is a random walk matrix that we have managed to write down.
And this rod G matrix is actually, I mean, everyone is, but this rod G matrix is very label dependent.
Yeah, it's very label dependent because like Varun was mentioning, the whole point started from the vantage point of every G vertex, you assigned the outgoing edges by some specific H vertex. Now, depending on that, your zigzag product may change, but you just say, take any assignment that you want, you get a corresponding graph out of that. Okay, and now I just want to get a sense of, how am I going to analyze this? And this is the part where we're going to, oh, sorry, I shouldn't be writing H, I should be writing MH. Which is the random walk matrix of H. Okay, just minor observation. Notice that all the rows of this matrix sum up to 1. Okay, all the rows of this matrix sum up to 1. all the rows of this matrix sum up to 1. So this is going to continue to be row stochastic and so on. Okay, good. So now what we are going to do is we are basically going to write MH in terms of the matrix decomposition. Okay, so this MH is going to be what is this going to be? So it's going to be gamma 2 times the all 1 by D matrix plus 1 minus gamma 2 times, I don't know, some error matrix. Okay, this was the matrix decomposition for MH, and I think I'm going to run out of space soon. So let me put it here, and I'm going to just plug that into the above equation. Okay, so therefore, mg zigzag h, this is going to look like gamma 2.
You said that all the rows sum up to 1 in I, the rows are summing up to 1 in image.
Yeah.
Tensor, you have to formalize I.
No, I is just, it's just going to be the, I mean, every row corresponds to one such, I mean,
Oh, it's I. Like
it's identity matrix. Yeah, it's the identity matrix. Yeah. Okay. So this is going to be gamma squared times, okay, I'll write down the main term and there'll be 3 other terms that will show up. Okay. So the first term is going to be I tensor J times rotation map times I tensor J. Okay, plus 3 other terms.
Distributed.
Yeah. Okay, all of these other terms will involve at least one copy of E. So it will either be of the form I tensor E times rotation of G times I tensor J or I tensor E, or the other way, maybe the I tensor E.
You just expand it.
So I'm just basically plugging in this equation into this. Just replacing MH with that. And there is a part that was a J only term. Okay, so that was this gamma 2 squared times I tensor J rotation map I tensor J. And then there's a bunch of terms, there are 3 other things which all involve some E there. Okay. Now, okay, so the first observation I want to make is that all of the matrices involved, be it I tensor J or I tensor E or rotation maps, etc., they all have spectral norm at most 1. Okay, some of them are really easy to see. Some of them maybe take a little bit more time. So rotation map, of course, has spectral norm at most 1 because the only thing it does is shuffles coordinates. Of course, it's not going to change length. So the rotation map being spectral norm 1 is of course trivial. Why is I tensor J have spectral norm at most 1? Well, one stupid thing is that it's actually row stochastic. So we already know that the spectral norm is at most 1, therefore. What about I tensor E? Let's get a sense of what does I tensor E really do. Like on each of those blocks, it's going to apply E throughout. Okay? And each of those blocks can only shrink in length.
I tensor J is not root stochastic.
No, I tensor J is the, I am thinking of J as the all 1 by D.
All 1 by D.
So J is, okay, maybe I should have put a JD here, in which case it's like 1 by D everywhere. Okay, so therefore that is row stochastic. And I tensor E is also having spectral norm at most 1 because per block the length only reduces. So overall the length can only reduce. Okay, so therefore all of these have spectral norm at most 1. Which means if I collect all of them and I don't know, call this some matrix B or something. Of course, there's some stupid gamma combinations of them. So, okay, let's just write down what this B is. So this B is going to be 1 minus gamma 2 times gamma 2 times I tensor E dot G I tensor J. Maybe there are two copies of it. I mean, I'm being sloppy here. I'm putting one this way, one that way, or something. Plus 1 minus gamma 2 the whole square. I tensor E rod G. I tensor E. Okay. This basically says that this has spectral norm at most 1. This has spectral norm at most 1. That's why I put a 2. It's not really 2. It's like the first one E is on this side, the second one E is on the other side. Matrix is not true, but I'm being sloppy here. Okay. Let me, since I have the ability to do a copy paste. Plus this will be a J and this will be a B. So these are the 3 terms that will show up. Okay. So this basically, the above observation says that this has spectral norm 1, this has spectral norm 1, this has spectral norm at most 1. So together, what can the spectral norm be? Like the sum of all of these things. It can be at most 1 minus, I mean, this quantity plus this quantity plus this quantity. Okay. And so this has spectral norm at most, the sum of the 3 quantities will turn out to be 1 minus gamma 2 the whole square. Okay, I mean, just that it's a convex combination, right? I mean, like, if gamma 2 the whole square is taken here, the rest of it must be split amongst those other 3 terms. Okay, so therefore, I can now write my matrix M G zigzag H as gamma 2 the whole square times I tensor JD times some rotation G times I tensor JD plus 1 minus gamma 2 squared times, I don't know, some, let me call it E tilde, where E tilde is this matrix that has spectral norm at most 1. I'm trying to keep it in the matrix decomposition sort of setting. Okay. And now what we need to get a sense of is we have managed to simplify stuff. Now what we are left with is this. Okay, so now the question is, what is this matrix? I tensor JD, take a rotation map followed by I tensor JD. Okay, so let's go back and sort of ask. We said when we are dealing with a graph H, what is the matrix that you write down for the zigzag product? It is I tensor the random walk for H, rod G, I tensor the random walk for H. What you have right now is I tensor JD, rod G, I tensor JD. So if I had to ask you, what is the random walk matrix for G zigzag product, the complete graph, you would have then said this is what it is. And in that case, we already saw that G zigzag product, the complete graph, is nothing but G tensor the complete graph. Okay, so it should be no surprise that this is actually, I should have written the other way. So this should be MG tensor JD. This is just a tensor product of whatever was the random walk matrix that you had for G, tensored with the random walk matrix corresponding to the complete graph on D matrices. Okay, so that is just MG tensor JD. And I mean, there are many ways to sort of see this. So let me just write one more. So let's say I am at a certain cloud U. Okay, and there are some, these are the vertices that you have. Maybe I am at U comma A. Okay, and all of them are connected now, and with self loops and so on. Okay, I just want to get a sense of what are we doing in this process. I mean, in these 3 steps. So the first thing I'm doing is IN tensor JD is like saying keep U as is completely randomize your second coordinate. So that is going to go to a random u comma a prime. And now what does RODG do? RODG says, well, there was one edge that was going out. Take that one edge. Okay, you are probably now in cloud B. Okay, and maybe you are at some vertex there. And again, this is also. And you put self loops. Okay, and now what do you do in the last thingy? You're basically saying stay in the same cloud, completely randomize the second one. Well, what happened in this entire operation? All you did was you took a random neighbor of u in the graph G. That was your first coordinate. And the second coordinate was just completely random. And that's the same thing as what MG tensor JD is supposed to. So we are saying that as actions, these two do the same thing. There are multiple ways of convincing yourself of this. This is perhaps what I think of as the easiest. Okay. Good. So this is done, and now we are almost done with the proof, and we are now going to use the matrix decomposition of G. This we know is gamma 1 times Jn plus 1 minus gamma 1 times, I am using the same E. Okay, or whatever, it's some error matrix, I don't care. Okay, so once again, if I substitute it above, what do I end up getting? I basically get, therefore, I tensor JD. I'll write MG tensor this game. This is nothing but gamma 1 times Jn tensor JD plus 1 minus gamma 1 times E tensor JD. Okay, and E tensor JD, I'm now going to call it, this is some, I don't know, E tilde tilde something. It's some other error matrix that also has spectral norm at most 1. So that should not be surprising. Okay, and now we are going to plug this into this equation.
So you get some D super tilde.
Okay, so this part will now get replaced by this part, which now gets replaced by this part.
Okay.
Okay, the only thing you need to keep track of is, like, this guy had a coefficient of gamma 2 squared. This guy has a coefficient of gamma 1. So therefore, this will say that M G zigzag H, this starts looking like gamma 2 squared gamma 1 times Jn tensor JD plus everything else will get clubbed up into one large error term. Okay, that is going to be 1 minus of gamma 2 squared gamma 1 times some E hat, where this guy has spectral norm at most 1. And this implies that G zigzag H is a gamma expander for gamma at least as large as gamma 2 squared gamma. Okay, so what did I don't know what I, okay. Okay, so this entire analysis basically lets us argue that the spectral gap of the zigzag product is at least as large as gamma 2 squared gamma. Okay, and we already saw that this was a graph on capital ND vertices. It had degree small d squared, and so therefore the zigzag product says this word. So the way you should think of what the zigzag product is doing is that it's increasing the number of vertices a bit more, though that's not really why you are doing the zigzag product. The main reason you are doing the zigzag product is to bring the degree down. And that degree is now independent of your original degree, capital D. It's now only small d squared, which is the degree of the inner graph squared. Okay. And as far as the spectral gap is concerned, if you imagine that you had managed to get a spectral gap of gamma 1, which is very large, what this now says is you now get hit by a gamma 2 squared. So your spectral gap reduces a bit. Whatever, maybe you had improved it a little bit and now it goes down a bit more. And the hope now is to somehow stitch all of them together to actually build our expander graph family. So what we are going to do, we are going to first increase the number of vertices and push the spectral gap down. Sorry, push the eigenvalues down as much as possible, but our degree will now be too large. So we'll do a correction step. We'll correct the degree. The spectral gap will reduce a little bit, but we will still be within the acceptable threshold, and we just keep repeating this. Okay. So in the next about 15 minutes or something, what I plan to do is to tell you how to construct an expander family, like using these 3 steps: powering, tensoring, and zigzag.
You start off with some simple expander.
You start off with some simple expander, and in fact, I'm going to start off with an expander that has this property. You will rightly say, where am I going to find this? But I will answer this question toward the end. But this, imagine like if you have a target D, or if you're willing to take D to be like 100 or something like that. This is some graph on constantly many vertices. 100 power 4 is a large constant, but nevertheless, it's a graph on constantly many vertices.
Brute force can find one.
Technically speaking, you can also do brute force. You can just try all graphs of this much thing and then find one expander there. Okay, but there are probably better ways to do it as well. But you start off with this base graph. Then you start off with something, and I'm going to tell you how to build these better and better expanders. So I'm going to define G1 to just be h squared. Just do the powering operation on G. What is the parameters here? So this is a graph on, of course, the number of vertices will not change. The degree will become d squared. Okay. And now this will be something. So this will be 1 minus 1 by 64. Because the eigenvalues, I'm writing it as 1 minus 1 by 8 to indicate that the eigenvalue was 1 by 8. That got squared. So it would have gone to 1 by 64. This is what. Okay. And G2 is basically going to be, I look at G1 squared, which is now going to be again on d power 4 vertices, but with degree d power 4 again. Okay. And that matches up nicely with the number of vertices in H. So I'm going to take this guy's zigzag product with H.
G1 squared.
Okay. So G1 squared is something on d power 4 vertices of degree d power 4 as well. So when I take a zigzag product with H, the new degree will be capital D squared. And the number of vertices will now just be d power 8. Because this had d power 4 vertices and it gets another.
It's basically that's called the J graph. I mean, I'm confused. D1 square has d power 4 vertices.
It actually has degree also d power 4. So at the moment it looks bad. But
it is not necessarily. No, I was just thinking, is it the J graph?
Yeah, it could be multi-graph. I don't know what H is. I mean, this is just a generic recipe.
Yes,
for,
probably.
Yeah, self loops and whatnot. Okay, and in general, I'm going to define GT plus 1 to be equal to GT the whole squared zigzag with H. So you should imagine it as saying that, I am doing a square to reduce the lambda, but I do the zigzag product to do both these things, increase my number of vertices and also to keep the degree back down. I know the zigzag product is going to cost me a bit on the spectral gap, which is why I'm improving the spectral gap before I do the operation. So that even after doing the zigzag, I still want to guarantee that if my previous spectral gap was at least a half, I continue to have a spectral gap of at least a half. Okay. So this is the graph family. This is how it's defined. And let's just briefly convince ourselves as to why this is the case. Yeah.
So each time you square, so for example, when you did G1 square, then your degree became d power 4.
Okay, so let's just do the following.
Right.
Okay, so this is going to be a graph on d power 4 into t plus 1, d squared and something. And I want to claim that something is at least a half. Okay, in general, GT will have d power 4t vertices. Okay, so GT squared will again have d power 4t vertices, but now have degree d power 4. And when I take a zigzag with H, I will have d power 4t times d power 4. That's the new number of vertices. the degree will now become the degree of h squared, which is d squared,
Slightly increasing the number of vertices every time by
by d power 4.
d power 4.
By d power 4 every time, and I'm getting some spectral gap. I mean, I want to claim that you get some spectral gap. Well, why is that the case? Actually, rather than let me do GT and GT plus 1. Okay. So now let's ask ourselves, what is the spectral gap here going to be? I'm assuming that this guy's spectral gap was at least a half. Okay. So lambda of G squared, GT squared is certainly at most a 1/4. Because the lambda of GT was at most a half. So I squared it, so it's at most 1/4. So what can I say about the spectral gap of gamma t plus 1? So this is going to be at least as large as there is a 3/4, which comes from the gap of GT squared times this quantity squared. Sorry, not this quantity squared. I mean, this was the spectral gap of H, so this is going to be times 7/8 the whole square. And it is set up in such a way that this is at least a half. Okay. And that's the reason these numbers were what they are. And so this tells us that if you know your original spectral gap was at least a half, one squaring and one zigzag is still going to make sure that your spectral gap is at least. Okay, but in the process, what we have gained now is that the number of vertices has gone up by a factor of d power 4. Okay, great. Now let's get a sense of, we wanted to know how explicit this graph family is. So how much time will it take if I were to ask you to compute some ath neighbor of a vertex u in the graph GT? I'm calling that gamma t for this. I want to know how much time will this take. So I want to sort of recursively try and compute how much time it would take to do this. So what do I need to do? I need to run 2 neighborhood computations in the previous graph. Okay, or maybe I should write this as gamma t plus 1. Okay, I need to do 2 computations of the previous graph, followed by, I don't know, some constantly many computations of the edge graph. And the edge graph is a constant size graph. So when I'm doing a zigzag product, that requires 1 computation here and 2 computations in this graph. But H is some constant size, so I don't really care about that. But the important thing seems to be this is twice the time it takes in the GT graph plus some order 1. And this is going to basically become 2 to the order t. Okay. Okay, now let's compare this with what the number of vertices is. How many vertices does the graph GT plus 1 have? Which is like roughly d to the t. And this is the same thing as like d to the order or d to the order t as well, which is basically poly in NT. Because the number of vertices in the graph GT is also exponential in t. There's just a question of, I don't know what the base of the base of the exponent might probably be different.
So twice time t to the order 1, then what do you do?
So if I solve this recurrence, I'm going to get something that looks like 2 to the order t. But that is basically polynomial in the number of vertices, because the number of vertices is also exponential in t. Because the number of vertices was d to the 4t or something. Okay. So yeah, and d is some constant here. But this means that this is only weakly explicit. Okay. That's a nice construction, but nevertheless, it's like the number of vertices isn't increasing fast enough for us to have a substantial gap between the computation time for the edge relation versus how many vertices the graph has. Okay. And in some sense, notice that we are not using the tensoring operation at all. In fact, one of the key points of the tensoring operation was that it gave you a way of increasing the number of vertices without taking a hit on the spectral gap. So maybe there is a way in which we can introduce the tensor operation also, and then build a slightly different family.
What was the con of the tensor product?
The degree increased again. The same con that we had for the squaring as well. But I mean, I don't want to rely on the vertex increase only because of a zigzag. The zigzag was not meant to provide vertex increase at all. That's like an extra side effect.
Contain the degree.
It was more to bring the degree down. So we shouldn't be relying on that for the vertex, number of vertices being larger. Okay. So now you do attempt 2, which is you now start off with a slightly different graph, which is like a d power 8 comma d comma 1 minus 1 by 8 expander. The reason is because I'll have to do a tensor product and then a zigzag, so compatibility will change a little bit. Okay. So once again, G1 is going to be h squared. And what is G2? I take a tensor product of G1 with itself, so that the number of vertices is now squared. Okay. And then do the previous operation. Take it square and then take a zigzag with h. Okay, let's just make sure that the compatibility works. And I want to claim that this is now this is going to be on d power 16 vertices. The degree is again going to be d squared and something. Okay, now why is that? Let's first, what do I know about this? This is going to be d power 8, d squared and something. That's what G1 looks like. Because I squared h, so I'll get a d squared here. So when I take a tensor, I now have d power 16 vertices.
Yeah.
Okay. Oh, am I missing something?
This will be d power 4.
So yeah, but this will become no. The
Oh.
tensor itself will become a d power 4.
But
then I take a square of that, so that will become a d power 8. Which makes it compatible with applying this thing.
No, I'm just saying G1 tensor G1 whole square. That degree will become, I'm fine with d to the power 16 there, but that degree will be d power 4, right?
No, it will be d squared again. D squared again. No, but I just think that this is not 16.
Why would it be d squared? Because G1 tensor G1, that will give you. So G1 had degree already d squared, right?
So G1 tensor G1 is now a graph on d power 16 vertices with degree d power 4 now.
Yes.
Okay.
Yes.
But then I'm squaring that graph.
Yes, so then it will become d power 8, right?
So this will become d power 8.
Yeah. Yes, that's what I was saying.
Okay. And now this is compatible with the zigzag
After
product here.
the weight, it will become d squared here.
Yeah. Once you take a zigzag with h now,
That's right.
it now becomes something d squared. So this looks like d power 24 or something. Right?
Yes, yes.
Because there is already a 16 that comes from this, and oh, maybe I'm messing up a little bit. I think my numbering is a little off. Okay, I might have to correct. So, but in general, what I'm going to do to define GT plus 1 is I just look at GT tensor with itself, square it, and then take a zigzag product with H. This is my new graph family. Okay. Something that's bothering me a little bit. So this is what I at the moment don't know. I don't know what this is going to be. We'll figure that out. But I want to claim that this new graph family that you have created, the number of vertices is going to increase rather rapidly. I mean, it's sort of clear that it will be at least d power 8. So this is going to be some d power 8t or something, because every time you do this operation, the number of vertices is squaring compared to what you had. So it will just become larger and larger.
But we are true to the exponent, because you're squaring and you're going to do it d times.
Yeah, that's what you need, right? Because you want doubly exponential is what will give you strong.
So okay, so here what I'm going to do is I'm going to do a t by 2 and this thing.
Yeah.
So let me write it this way, because this is a calculation is going to become a little easier. So if I define GT to be GT by 2 tensor with GT by 2, square that and take a zigzag with
No, but
this
don't
thing.
you want a double exponential in the number of vertices? You do. No.
No,
Oh.
so this should be fine. So anyway, let's go over this thing. And this, I guess, this will now be something like d power 8t and D squared comma.
Recursion will work on T by 2.
Yeah,
That will give you this.
yeah. Okay. So let's get a sense of firstly, what is the number of vertices? Okay. So the number of vertices is basically going to be the number of vertices of T by 2, the whole squared, times the number of vertices of the graph H. Okay. I mean, I'm just going to put at least this much. So this is going to be at least n T by 2 is I'm claiming is at least n8 T by 2, the whole square times d power 8 or something. So every time it sort of actually is going up by at least this much. So the exact number of vertices, I don't care as long as it's exponentially increasing with t. Okay. And the gamma calculation is exactly the same. So lambda of gt, suppose, or gt by 2, suppose this was at most a half. Okay. Then this implies that lambda of gt by 2 tensor with gt by 2. This is also at most a half, because tensoring does not change the spectral gap, which means when I square this, this is going to become at most a 1/4. And this is therefore going to say that the gamma, whatever t, is going to be at least as large as 3 by 4 into whatever 7 by 8 the whole square. Same thing as before. 3 by 4 into 7 by 8 the whole square, which is set up so that this is at least half. Okay. So yeah, so good. So this is the so the next thing we want to get a sense of is like how much time will it take to actually compute the. So same thing as earlier, but now what we need to do is I need to. So in order to do one edge relation in the graph GT, what do I need to do? I need two edge relation in this tensor graph, plus some edge things. The edge things don't matter. But two edge relations in this tensor graph is like 4 edge relations in GT by 2. Because every step in a tensor product is like I need to take those 2 steps. And if I'm doing a square of that, okay, there are 2 steps of this and 2 steps of this. So there are 4 computations of GT by 2. So in this case, you now have this is 4 times time of t by 2, again plus some order 1. And this, fortunately, this is poly in t, because it looks like 4, this is going to look like something like t squared or something. Okay. But on the other hand, the number of vertices was exponential in t. So this is polylog in NT, because NT was like exponential in t. And therefore, this is a strongly explicit family. Because, I mean, this is an example of a family where computing the edge relation is significantly faster compared to the size of the graph. The time you take to compute this is way smaller than the time you take to write down the graph. So it's logarithmic in that. Okay, is this okay? There's one annoying catch, which is that the way I have defined it above, now it depends on what I mean. So from G1, I was able to define G2. From G2, you will now be able to define G4. From G4, you will now be able to define G8 and so on. Which means you don't really have GT for all possible choices of T. You only have them for powers of T. So the double exponential, in terms of number of vertices, it will sort of tell you that I give you a family, but the number of vertices is sort of too sparse. So because like in the sense that there's going to be some graph on, let's say, d power 8 times something, and the next one is something much larger than that. So in the sense that I don't have graphs for lot of degrees. So there's a very simple.
Every constant factor.
It's not a constant factor, unfortunately, because So yeah, you have a d power 8 times 2 power k. The next one is like d power 8 times 2 power k plus 1 or something.
Oh,
So the number of vertices is increasing too much. So if you were unlucky and you wanted something that had this plus 1 vertices, I will end up giving you something way larger than that. So that's probably not what we want. Okay, and there's a simple fix, which is the following, which is to use some floor and ceiling to get what you want, basically. Okay, so you define GT to be equal to, you take the tensor product of the right things. You look at the floor of t by 2 and the ceiling of t by 2, take their tensor product, square it, and take the zigzag with h. Okay, you just need to sit and check for yourself that the compatibility works for the zigzag. The calculation for the spectral gap, etc., is exactly identical. But now you have an option of, you can now define what G3 is. So what is G3? You take G1 tensor with G2, square that, take the zigzag with H. So G3 is also now, so you now have GT for all possible T. And now this truly grows as, I think, 8, it says some d power 80 sort of thing that will happen. And it will tell you that if you are interested in a certain number of vertices, I will be able to find a graph that has roughly that number of vertices. I might have to pay something like d power 8 in the factor, but you will get graphs for almost all, I mean, sort of very reasonably spread out. I mean, it's not something that is like they're too far apart or something. Okay. So what this above family is it gives you a family of d squared regular graphs. Okay. All the graphs that we constructed here were d squared regular. You have a guaranteed spectral gap of at least a half. And they're all strongly explicit. And you also have a graph of the right size. Like for every target size you want, you will find a graph of roughly that much size. If you're willing to pay like a d power 8 or something, you'll be able to find. So yeah, and now finally, there's this thing of, how the hell am I going to find these sort of base graphs that you have? There are two options. So the first option is this brute force.
You can also use my LPS.
Yeah, but in the sense that I don't want to use something that I can't prove that it is an expander or something. But I mean, you could sort of, do LPS in the following sense. You anyway care about it only for constantly many vertices. Write down the graph, look at the spectral gap, and then do something. You just compute the eigenvalues for it. But okay, so this is the first, the first option as to how do you find this H. Of course, it's not a nice option. The second option is in problem set 2, which will hopefully soon come out. And it's a very nice graph that I am going to describe right now. And proving that it is an expander is actually very easy. Okay, that's so that you have a completely self-contained proof for this. Okay, what is this graph? This is a graph on p squared vertices. Okay, choose p to be a prime. In this case, I just need to choose a prime. This is a constant, so I can find that there's no explicitness is not a problem. And I'm going to think of the vertices as a comma b, where a and b are elements in fp. Okay, and I'm going to take two different views of what this a comma b refers to. The first view is that a comma b is a point in the plane. That is, imagine the plane fp squared, just imagine that as being a point in that plane. And the second interpretation I'm going to think of, so this is the point, is that I'm going to think of this as a line y is equal to ax minus b. So the set of all points that satisfy this equation, y equals ax minus b, I want to think of a comma b as either the point or the line. There are two slightly different perspectives that you could have. And what is the connectivity? So I connect a comma b with c comma d if the following holds. which is I want AC to be equal to B plus B. So that it's a symmetric relation where AC equals B plus D. And you can interpret this as saying that the point A comma B lies on line C comma D. Okay, that's a different way of interpreting this edge relation. Okay. Now notice that every line will contain P points. So if I ask how many vertices am I connected to, you immediately get that this is a P regular graph. It's not P squared vertices, it's P regular. But the nice thing about this is that you can actually show that its second eigenvalue is 1 by square root P. Okay, and it's not hard at all. And this is what we'll have in the problem set. So this is like, I don't know if this graph has a name. Like I used to call it the affine line graph. It's like the line point incidence graph in some sense. And so now that you have like a decent expander, you can now play around with your powering, tensoring, and so on, and get whatever you want from it. Like that part, you will have to try out your own way of doing it. Vadan has, in Salil Vadan's notes, he starts with this graph and tells you how to build this d power 8 comma d comma half sort of graph that you wanted by a couple of operations on top of it. But this proof is actually very nice. And this geometric view really helps a lot. And this is one of the things we'll see in the problems. Okay, so with this gives a complete construction, like fully strongly explicit construction of expanders, strongly explicit graphs and strongly explicit proofs of saying that these graphs are good expanders. And in the next class, what I will do is use these explicit graph constructions to prove Reingold's theorem, which says that undirected ST connectivity is actually solvable in log space. And there, the LPS graphs, etc., will not be helpful. It will be very important that you start with a graph and it gives you a process of making that a better and better expander. And that's what we will use in Reingold's. Okay, cool. So I'll stop here. Hopefully by the weekend, I'll put a problem set too.
So
Yeah.
there were two operations. There was squaring, there was tensor. So if there was an operation that, so this was an operation where you did reduce the degree, but you actually changed the graph. Right?
So which one?
So suppose that we do the sequence of operations, squaring, tensoring, and then let's think of this as a degree reduction.
The degree reduction thing, yeah.
But degree reduction here actually changed the graph, like the number of vertices.
The number of vertices actually went up. Yeah.
Are there, like, can one think of an operation where you keep the number of vertices the same in some sense, or maybe reduce it a little bit, but change it. So I mean, the parallel to codes is that this degree reduction is like some sort of puncturing.
Yeah.
But this operation is nothing like the standard.
It's a good point.
Are there ways of reducing? So given a graph, I don't want to change the number of vertices. I want to keep it the same. I want to reduce the focus on a subgraph, which maybe I am willing to take a little bit of a hit in the expansion.
So the part that I'm trying to get a sense of is, so I still need, so whatever was the old edges in my graph, I still want to encode those edges in my new graph. So in some sense, there are that many connections I still need to keep track of. But somehow it feels like if I want the degree to be low, I'm not able to think of a way besides increasing the number of edges.
Following would work. It's not explicit, but suppose you take a graph G, which is capital D regular with some good expansion properties. And now we just subsample the graph. Right? At every vertex, we drop the degree by a factor 2. I'm guessing that we should be able to prove a lower bound or an upper bound on the second eigenvalue. I don't see how to do it immediately, but because this is a random process with reasonable probability, this is almost like
what we would do in codes.
Yeah.
Okay.
So maybe this is like a randomized way of making your graph sparser but maintaining connectivity in the expansions.
So your idea is if the graph was a random graph, this would work. Right? If it was a good expander, then it should work.
Yeah.
Also.
So, I mean, so in some sense, like in general, there are these constructions of what are called graph sparsifiers. So I think this one of the things I initially wasn't thinking of doing it, but I can maybe do it if there's. So the thing is, it was I think originally defined by Bensor and Kargar, where they wanted to compute some cut computation. But you have a graph and you probably are interested in cut sizes between two vertices. And Bensor and Kargar basically they showed that if you subsample your graph but keep it sparse, that is you only have order n vertices, then you can do it you can show that your cut sizes will only increase or decrease by a factor of 1 plus minus epsilon.
Order n edges.
Order n edges. That is irrespective of how dense your graph could have been. You now resample, but obviously you have to reweight your edges appropriately. But you now have a sparse weighted graph such that the weighted cut size in your sparse graph is within a 1 plus minus epsilon of the cut sizes of your original graph. So the stronger version of this was this notion of what are called spectral sparsifiers, where you basically say that I want the eigenvalues of my new graph to be within 1 plus minus epsilon of whatever eigenvalues I start off with. And spectral sparsifiers are also like in the sense that if you want a 1 plus minus epsilon, you can it suffices for you to take, I think, order n over epsilon squared edges. But this is it's not a random sampling. Like it's there is
randomness involved.
Yeah, there is randomness involved, but it's like you need to appropriately reweight some like there are some edges that will just be crucial for you. Like for example, if your graph is a dumbbell graph, you can't afford to lose this edge because losing this edge will suddenly make your eigenvalue 0. Eigenvalue 1. So you don't want to do that. So there are ways of but somehow I'm wondering if there is a way of interpreting that as because the number of vertices don't change. The vertices stay the same.
That's what I'm asking. That's closer to what how I would think one would do it for codes.
This is the Spielmann Srivastava.
Yeah, so I think it was first Batson, Spielmann, and Srivastava. They showed that I'm forgetting which was which. There was one where there was a random sampling process where you have an additional login factor. And then there was a second paper which basically said, no, if you're a bit more careful about it, you don't need this extra login factor. There are graphs that are order n over epsilon squared sparse, that are epsilon spectral sparsifiers or whatever graphs you started off. That is, all the eigenvalues will be within 1 plus minus epsilon. Yeah. Okay. So
what would be the advantage of it for this thing?
It seems like a natural operation. I just don't see.
In the sense that it the role of the zigzag was to reduce the degree, but somehow we are having a side effect of. So, for example, this actually will start happening. This will become important in Reingold's thing. Like, if there was a convenient operation of that sort, I think Reingold would have become easy. So the thing is, one of the things that happens in Reingold is that you want to do ST connectivity on an original graph. But in the process of expanderizing the graph, what will end up happening is the number of vertices will keep increasing. So you need to have a notion of, look, I wanted to do ST connectivity in my graph G. Now you have given me a different graph, which is not on the same set of vertices.
Connectivity property has to
yeah, but connectivity of what? So you need to have some notion of mapping the old connectivity to this thing. So it just complicates it a little bit. But had the number of vertices stayed the same throughout, then probably we needn't have worried about that issue at all. It's not a problem, but in the sense that it would have just been nicer.
Oh, okay. I mean, had the number of vertices stayed the same starting from the given graph?
Starting from the given graph. So here what will end up happening is that your final graph on which you will actually run your algorithm, there are these clouds. Each original vertex has become this large cloud, and you're going to ask, is that cloud reachable from this cloud? Rather than doing actual ST connectivity.
The spectral sparsifier thing is randomized, is it? It's not.
Yeah, it's randomized.
If there was some deterministic way of achieving that 1 plus minus epsilon, your eigenvalue stays the same, but your degree goes down. That was what Spectral factor.
Yeah, but I'm sure there are some de-randomized versions of spectral classifiers. I mean, I'm saying it's randomized, but you know exactly what edge to take, and you will know whether taking this edge is it good for you or bad for you. So it's a really beautiful, it's a very physical algorithm in the sense that you sort of say that every edge, the importance of the edge is like you imagine your graph as an electrical network and you look at the effective resistance across this edge. If that is like, depending on the effective resistance, you know how crucial that edge is. And now you sample edges, you sample order n over epsilon squared edges, but weighted according to this. And that's the algorithm. It's a really clean, really beautiful algorithm. Actually, I don't know now am I describing Batson Spielman Srivastava or Spielman Srivastava? One of them. Yeah.